So a warm good evening to everyone present today. So my name is Abhinav. I am working in Decibels Lab as a BMS algorithm development engineer. So my work basically includes creating digital twins and basically mathematical models of lithium-ion batteries and cells. So basically, the primary objective is that we subject the cell model to different situations like different temperature, different current, or different voltage profiles, all these things, and we see the outcome of that simulation, and then we try to integrate that as a whole battery pack model, and then we're able to see the behavior of that model in many different situations. I've also have worked on cell testing and characterization, so where I have taken a lot of cells like lithium ion cells, and I have subjected them to different types of tests, and obtained like a lot of parameters from them, like aging, thermal test, or a high C rate and low C rate discharges, all these things. So apart from that, I have also developed BMS algorithms like SOC and SOH estimation algorithms. So in today's webinar, we'll be exploring just one of those algorithms called as state of health estimation algorithm using Kalman filters. Okay, so Kalman filters is like one of the most widely used estimation algorithms in today's EV market. So lot like one of the most sophisticated estimation methods, which is like promises to bring you like really good results. So we'll be seeing in this webinar just like how exactly we can use the Kalman filters. So we'll also be having a quick overview on the model. So there is a Matlab Simulink model that is prepared here, and we'll be having like a quick overview of that along with like the necessary algorithm. Yeah. So we will look at today's content. So what all today's content includes. So this is the agenda for today. So first we will start with the necessity of estimating your state of health. So why is it important to go for state of health estimation? So in an EV, so we trace so many parameters. One of them being the state of health. That is, you can say the condition of the battery. So, but what is the necessity of estimating this state of health? So after having explored this, so also we'll just go into like some factors, what can cause like deterioration of the cell, what are the main reasons for the cell and battery pack degradation. Then we'll go into like in today's market, which are like the one of the most commonly used different SOH estimation methods. So like Coulomb counting, least squares method, something called as charging curve analysis, Kalman filters, which is today's topic, and also something called as impedance tracking. So just we'll have a brief overview of these methods. And then our next focus will shift towards Kalman filter for state estimation. Okay, so first we'll understand what is Kalman filter for state estimation. Then we'll proceed into the other part where we're going to be estimating the state of health. So for that, we'll require an additional set of Kalman filter called as the Kalman filter for parameter estimation. So that portion comes a little bit later on in the session. So after that, we will like try to understand what are the cell parameters which are going to be estimated to get an idea on how SOH is estimated. Because like SOH is, these are all indirect methods, SOH is indirectly estimated. It's not a direct estimation. So for that, what are all the parameters that have to be first estimated? We will see that. And then we'll go into the model overview where I will show the Matlab and Simulink model. So there is a readily built model that is available. So we will be going through that. And then I will perform a basic simulation where you can see the change in SOH, change in resistance, and also in the state of charge. Okay. So this is today's agenda. Yeah. So yeah, I suppose it's, I'll resume.
Yeah, please.
So first we'll just have a quick look at why the estimation is important. So state of health is just simply defined as your relative condition of the cell to the fresh condition. So currently, what is the condition? You can describe the condition as anything, either in terms of capacity or internal resistance, or even as energy capability, capacity retention ratio. So these are all different ways in which you can define the present condition of the cell. So on the left side, you can see a very simple like a representation of how the cell goes on degrading. So first, of course, you start with 100%. So how do we measure the initial capacity? So we go for what is called as a static capacity test. So this static capacity test is a measurement test which is like done using a cell testing machine or a battery pack testing machine. So basically, after subjecting it to a standard discharge C rate and a standard charge C rate, the average capacity measured in both the situations will be recorded as the beginning of life capacity. So BOL, you can see here, BOL is the beginning of life. So the capacity from there onwards will go on decreasing as and when you keep subjecting it to like different situations. Various such factors could be there, like temperature. The temperature could be a like important factor that decides how quickly or how slowly the cell goes on degrading. The other one could be your C rate. So other environmental conditions are also there, like humidity, condensation, or water vapor. So high temperature could cause like rapid degradation. Even cold temperature can cause rapid degradation. Fast charging and very fast discharging can also cause faster degradation. Manufacturing variations are there. So these are all your you can say important influencing factors for state of health. Basically, this will affect your total shelf life of the cell, or you can say a total uh, operating life of the cell. So usually for electric vehicles, whether you take four-wheeler EV or even the two-wheeler EV, around 80% of your measured capacity will be considered as the primary life, the end of the primary life. Okay, so you can see here end of life. So after that, there will be another set of reference performance test conducted. So it's called as a reference performance test. So this reference performance test, this is basically a set of tests that will be conducted at the uh, like at every intermittent, you can say like cycle number. So like for example, every 50 cycles or every 100 cycles, once the battery completes this interval, a set of reference tests will be performed to check the current condition of the cell. So this is also performed at the end of life. So approximately when the cell has been estimated to have reached around 75 or 80% capacity, it will be subjected to another series of tests where the future usage or usability of the cell and the battery pack will be determined. And based on that, we'll also go for secondary life. So like there are many like startups and other different organizations which are like currently like providing funds for like battery pack and cell recycling, where they take like older cells which have reached like 80% capacity, and they're like reusing them for like secondary applications like energy storage and things like those. Yeah. So, but why is it important to monitor the state of health? So, the most important reason is that we need to know the battery health indicators. So, in essence, like the two most important battery health indicators are internal resistance and the capacity degradation. So these two are like very important battery health indicators. So if we are able to derive and determine these values during the real-time usage of the cell or of the battery pack, then we're able to determine your service life, or you can even say shelf life. The shelf life is basically like how many cycles is the entire battery pack rated for, or you can also say in terms of years or months of usage, right? For example, if you in India, if you take the example of Tata Nexon, they come with a total service life of around 8 years or 8 lakh kilometers of total usage. So basically, the battery health is estimated so that we are able to you're able to determine how long the battery will last, and also several other parameters like in terms of even on the customer side. So when can the customer go for battery pack replacement or a battery pack readjustment or recalibration, so that it is able to like extend the life a little bit more. So these are all like options available from the customer end, so that they're able to understand and make the best use of their car. Yeah. So that is the main reason why battery state of health is very important, because it gives you a good idea of when the battery pack will reach the end of service, and also like when the battery pack will require further servicing. right? So these are the important points of why like SOH is important. So coming to like the different SOH estimation methods, so there are actually like many algorithms that have been introduced so far. So in this like webinar, we'll just be like seeing in just like a brief picture, like what are all the different ones that have been introduced so far. So the most commonly used ones are listed over here. So like Coulomb counting. So basically, we have the current signal sent from the current sensor. So current sensor will like it will gather the current signal into the battery pack, and from there it will undergo integration. Okay, so continuous integration it will undergo, and once like the integration is complete, we have what is called as accumulated charge. Okay, so either in terms of discharge or in terms of charge. So you can like count how much charge in terms of like ampere hours or amp seconds has passed through, and over the number of cycles, the accumulated charge will go on decreasing. So that is one way in which you can actually measure the state of health of the battery. So like we can say like one full charge and then one full discharge is one cycle. So one charge and one discharge. So if you take one full charge and one full discharge, that is one cycle. And in that one full cycle, how much charge has been accumulated, how much charge has been passed through, how much charge has been put back inside the cell, you can calculate that using the integrator. So over the cycle number, the charge accumulated per charge cycle or per discharge cycle, it will go on reducing. Yeah. So that is like Coulomb counting method in like how you can measure the total change in capacity of the cell. So you can also go for another way. It is called as using least squares approach. And one of the like most widely used method is called as weighted least squares. So basically, you again collect the amount of current passing through the current sensor, and again it undergoes integration to give you the amp hours. So you can see here the y-axis actually corresponds to the integrated current in ampere hours, and here on the x-axis it is the total change in state of charge. So here an additional parameter comes in. So change in SOC. Change in SOC along with your total integrated current, which is an ampere hours, will give you somewhat of a linear graph as you can see here. So like on the bottom, you can also see like what kind of polynomial has been used for curve fitting here. So basically, this is nothing but linear regression, right? So this is one way in which you can like analyze the slope of the curve and then determine the capacity of the cell. Okay, so like each time the cell goes on aging, the slope of the curve will go on changing. So as and when the slope changes, even the estimated capacity also will go on changing, right? So you can make this fitting, this linear regression part more accurate by changing the weightage, and then therefore you can observe the results over here. So basically there's a parameter called R square. So this is all part of like statistics. So and RMSE as well, root mean square error. So like if these values like get closer and closer to like if R square gets closer to 1 and RMSA gets closer to 0, that means your capacity estimate is like very accurate. Okay, so we can do that by changing the weights, providing like individual weights. So weight is nothing but like a simple function where you are basically guiding the fitting equation towards the correct deviations. Okay, so like you can prefer whichever deviation you want, whichever deviation you feel is the more correct deviation. You can put the weighting function in that way and improve the linear regression approach. Right. So this will give you another estimate of capacity. So this is one way using the weighted least squares. So there are more advancements to this as well, using what is called as adaptive weighted least squares or forgetting factor weighted least squares. Even like other nonlinear least squares approaches are there. So basically, they're all extension to this particular method. So weighted least squares. So pretty much, the algorithm for that is the same. You're going for regression there also, but there you can like add some extra like adaptive algorithms which will adjust automatically according to the trend line in the distribution of data. So these are the two like commonly used methods. apart from that, we also have like charge capacity estimation using your charging curve analysis. So like this is more like towards the practical application. So basically, we know that EVs have to like undergo charging every time the battery is like near 0%, right? So there is a method of charging called as CCCV. So CCCV charging is like more or less like standardized throughout the entire EV industry. So uh, so one particular trend is observed over here that as and when the like battery cycle number goes on increasing, the there is an effect on the CC and CV region. So you can clearly see here. So when it's in the fresh condition, so this portion is in the fresh condition, and this part is in the like aged condition. So the difference between the fresh and aged condition is you can see here that the constant current region will go on shrinking, or you can say it will go on reducing. So meanwhile, the CV region will go on increasing. You will notice that that kind of trend line is there, where it will like even the CV region is affected and it will go on increasing. Right. So this is another battery health indicator, and this can be used as a function to estimate the state of health. So like you can see here, over like a large number of cycles, about 1,500 to 2,000 cycles, the complete charging curve has been like established. And every time the cycle number increases, you can also see that your CC region, that is your constant current region, will go on decreasing. So this is one way in which your state of health can be used. But one challenge is that you cannot go for charging curve analysis if the charging is an incomplete charging. Like for example, we are charging only from say for example 10 to 40%, or maybe something like 30% to 60%. That is actually going to be a setback. So the complete curve from 0% to 100% should be available, and then you can like say that the entire state of health is changing because of the change in CCCV regions, right? So the other one is capacity estimation using extended Kalman filters. So like we have Kalman filters that will estimate the state, and also a Kalman filter that will estimate the parameters. So we have two Kalman filters that will function together. So basically they'll act simultaneously and they will produce the required state of the battery, that is state of charge, or the desired terminal voltage, the required voltage across the RC circuits. This is one portion. The other portion is the parameter of the battery, which we'll be exploring, like that is the internal resistance and the capacity, right? So that is like the purpose. Kalman filters actually is like one of the more like chosen or more preferred ones, because always consistently it will give the required results. So later on, as and when we progress in the session, we will see like bit by bit the structure along with the algorithm. So, and also we have one combined approach, which is called as impedance track method. So this method actually has been introduced by Texas Instruments. So they have developed a BMS, or you can say a BMS solution, where the capacity of the cell can be estimated utilizing the Coulomb counting, that is the total charge that has been estimated using Coulomb counting, and the change in state of charge using the SOC OCV lookup table. Okay, so this is the SOC OCV lookup table. And here you can see here like even the temperature influence has been considered, right? So the temperature profiles from 40 degrees to about 0 degrees. So all these OCV profile has to be considered. So along with this and along with the Coulomb counting put together, you get to estimate the capacity of the cell. Basically, you are calculating the total charge passed, delta Q, and the total change in SOC, delta SOC. So utilizing the relationship between these two, certain parameters like the remaining capacity, the starting capacity, like the leftover capacity, all these things can be calculated, and from there, something called as FCC, or you can say full charge capacity, is available, which is your final capacity of the cell. So that can be used as an indicator for state of health, right? So this has actually been introduced in the BMS in today's EV market. Like there are certain vehicles that use the Texas Instrument BMS, and they actually go for this approach using the impedance track method. Yeah. So these are like so many different approaches that you see in today's EV industry, then most of these have actually already been implemented and tried and tested, and majority of these are actually in I can say most of them are reliable. Yeah. So today's focus will be on the Kalman filters. So before we progress on to the further topics, so there will be a quick poll of just about 2 minutes. So I request my colleague Vinayak to start with the second poll. So just please do go through that and yeah, just answer what you feel is the best.
There's only three questions are there, so kindly attend all the three. Okay, we'll just not spend too much on this pool.
Okay, just 2 minutes.
Few participants just participate. I request who has not yet answered those taken the poll, please take it. I can see 9 others have not taken, and thank you for those who have taken it.
Yeah, I think Vinayak, we can move to the next section. Right. So thank you, the participants, for taking that quick poll. So, amongst all the methods that we see here, yes, the simplest one that we can go for, or you can say the most preferred one, is Coulomb counting. So that is very simple to implement. It does not require much computational power and does not require very depth knowledge of some mathematics or anything. So very easy to implement, very easy to convert as a code generation in case of real time application, even in terms of hardware. It is not very demanding. So Coulomb counting is one of the most preferred. Yeah. So that being said, we will then move on to the next section that we have. So that is your Kalman filter algorithm for state estimation. So first we'll have an overview of this, like how exactly the Kalman filter goes for state estimation. Then we'll try to understand how parameter estimation is done. So here on the right-hand side, you can see the complete steps, or you can say the flow of the process, how the Kalman filter will start. So first we will start with initialization. So whichever filter we have, whether it's recursive least squares or if it's a Kalman filter, a regular linear Kalman filter, an extended Kalman filter, or a sigmoid point Kalman filter, whichever it is, it always starts with a certain initialization where we provide some initial guesses. So like we have to provide the starting point for the filter. Okay. So here you can see mark the step number 1. And here you can see like we say initialize certain values. So here we are going to be initializing things like the noise. So noise is basically like undesired deviations, or you can say variations in the signal. So noise and initial certain parameters are there, initial parameters, right? And even we have to define the initial capacity as well, so that it is able to accurately estimate the states later on. Okay. So when we come to this particular word called states, we have so many states. States is basically a variable of a system that defines the particular, or you can say the present condition of the entire system, or you can say the behavior of the entire system. So the states, in case of like Kalman filters, the states has been, you can say there are two states. One is state of charge, SOC. So this is one of the estimation parameters. And the other is what is called as voltage across RC circuit. Okay. So these are like the states of the entire system. So we will not explore like the derivation of these states because that is right now not part of today's scope. So after like considering some complex system dynamics and understanding how cells behave using the input output relations and the state equations and things, we are able to come up with a like different states. Like what are all the major factors, or you can say major variables that play a role in the system behavior? The state of charge and voltage across RC circuit, right? So those are the states, and that is basically what we see here, initializing the states. So once we start with this, we then proceed to like step number 2, so which is basically prediction. Okay, so in prediction, basically it's a step that is used to predict the future state, or you can say the next value. Basically, it is like a way in which we are projecting the current value to the next value, okay, using the past value. So that is prediction. For when the Kalman filter begins the execution, it has to consider the starting point as the previous value, and as and when the loop continues, or you can say as and when the execution continues, the prediction, or you can say the next value, will go on changing based on the present value and the future value. Yeah. So that is the state prediction part, which is on number 2. So along with state, there is something called as uncertainty. So uncertainty is like a degree of like variation, or like basically you are unsure whether the how much error is present in the predicted state. So we have to also mention something called as uncertainty. So once we have that, so both of them simultaneously get updated in this step called as state update. Okay. So along with this, we also have to estimate something called as Kalman gain, which is like very simply, it can be defined as a weighting factor. So weighting factor is basically you give a preference to whether you want what kind of preference you want, whether you want more preference towards the predicted value or towards the measured value. So if you have this Kalman gain, along with that simultaneously you have the state update. So once you have the updated state, we have what is called as the current system state. Okay, so the true value of state of charge will be seen here in the outputs. The true outputs, you can say the true SOC, and then you can also say true voltage across the RC circuits. Okay, so this part, the second part, the voltage across the RC circuits, it depends upon what kind of model complexity we are considering. So whether we are choosing an equivalent circuit model of 1 RC or 2 RC or anything like 3 RC, it is dependent upon that. So accordingly, even the VRC contribution will change. So if you're having 1 RC, it becomes voltage across RC1. So if you're choosing 2 RC as a method of estimating your voltage, then it becomes VRC1 and then VRC2 as well, right? So that there is a small part where we'll be covering on the equivalent circuit model as well. So that is there in the next slide. We will see that. So once we are done with the Kalman gain, we have to define what is called as error. So that error is nothing but the difference between the observed value and predicted value. Right? Observed and predicted value. So that error is basically what will be feeding in this portion, in the state update part, along with the Kalman gain, to get you the exact current the current system state. Okay, so like this is how basically the states are estimated. So this update is also called as correction. So basically, correction also means you're correcting, or you can say you're rectifying to the actual value of the state from the predicted value. So you're basically bringing the predicted value closer to the truer value. Okay, and that is how your Kalman filter or your extended Kalman filter will go for state state estimation. So along with this, there are certain other things like defining the observation matrix. This is also called as Jacobian matrix. This Jacobian matrix is basically you because there's a certain degree of non-linearity within the system, and if you're representing this as a linear term, then you have to go for observation matrix, where you are representing the non-linear term as a linear term. Okay, so using all this, we are going to go for state update and uncertainty update, and then finally you arrive at the current system state. So this entire loop, starting from step number 2 all the way till step 5, this will be run in a continuous loop. Okay, so this loop is basically, it will go on till such time there is convergence. Okay, so there will be a certain factor, or you can say a certain point where the estimated value from the Kalman filter will merge, or you can say it will converge with the true value, or you can say the measured value. So till such time the convergence has been obtained, this loop will keep on running. Okay, so that is how the entire state estimation algorithm from Kalman filter will work. So based on this you can say the very nature of Kalman filter, we will even go for parameter estimation. So we'll be coming to that in a quick while. So first we'll look at like just a brief overview of what exactly is meant by error definition and the RC circuit's preference. Okay, so whether you are preferring one RC circuit or whether you're preferring two RC circuit, it purely depends upon the complexity you want, or you can say model fidelity. So here you can see there are two different models. One is called as 1RC model, one is called as 2RC model. So basically, these are like equivalent circuit models. So it's also called as equivalent circuit model because you are representing the cell as a electrical circuit here. Okay. So like you can see here, like one resistance in series, the other resistance in parallel along with the capacitance. So or you can represent it as a series of two RC circuits as well. Okay. So this is one RC branch, just one RC branch. And then here you can see there's two RC branches. Basically, there is variation in the RC branches because you are categorizing the internal resistances in like different formats, or you can say in different ways. So that's why you're able to see like either one RC or two RC. So it is purely left to the model simulation engineer, which like a degree of complexity you want to choose for the simulation. Right. So here on the right hand side, you can see something called as error calculation. So there are two things you have to consider. Basically, this error is nothing but the difference in your measured value versus your predicted value. In case of model in loop, so I'm talking about model in loop. Model in loop is nothing but simulation only on the software, not in real time. So in this case, the error is calculated as terminal voltage, which is taken from a reference signal minus the terminal voltage from a predicted value. So that comes from the state prediction. Okay, using this error itself, the state correction is done. But in real time, you will notice that your difference is like terminal voltage from the voltage sensor, which is in real time, minus the real time predicted value. Okay, so that is the difference between the error calculation in both cases. So in real-time application, we will not be using like one RC or two RC. It will be like data will be coming from the cell or the sensors from the cell, or even for the battery pack. Yeah. So this is the like purpose of using equivalent circuit model. So basically, this will be used for like estimating your error. Okay. So now we know like some very fundamentals of, let's say, Kalman filters. So what it does in terms of state estimation, in terms of like error calculation, state update, and things like that. So now we have this extended part, or you can say an extension to our existing Kalman filter model, called as Kalman filter for state and parameter estimation. Okay. So there are different names you can use for this. One is called as dual extended Kalman filter. Just abbreviated as DEKF. Then you can also call as SPKF, sigma point Kalman filter. You can even find as adaptive Kalman filter. So these are all just slightly different variants of the existing Kalman filter or extended Kalman filter. So they are just in different formats. Yeah. So here we are already we have till now we have seen how the state estimation is done, right? Using like three important steps, that is prediction, using the Kalman gain, and then the correction or the update. So there is an extension to this, or you can say a second part to this, where we are estimating the parameters using a similar set of processes, where we are going to initialize the parameters. Okay, so we are going to initialize the parameters of there are two parameters. So one is cell capacity, and second one is going to be internal resistance. Yeah. So these are the two parameters that will be initialized, and then again using the same set of like logic, that is prediction, a correction, or you can say update along with the Kalman gain. So same process is followed. So here, like the symbols, only the symbols will change, where you have theta and S instead of X and P. So X and P is used for state and uncertainty. Theta is used for parameter uncertainty. Okay. So here you can see the complete flow. So one thing to note is that these entire set of steps will run simultaneously. So this they're always running parallel to each other. So this portion we have discussed, where we are going to go for state estimation. Here in the second part, we're going to go for parameter estimation. So in the similar process of how we are doing state, we'll also have to go for parameter estimation. So initializing the parameters, so like putting some input guessing, some input guesses or input values. So once we go for input guesses, we then go for prediction. Prediction, then going for Kalman gain. So this is like parameter Kalman gain, then parameter update, and then outputs. So similar to how we have the state estimation. Yeah. So based on this logic itself, we have a Matlab Simulink model, which I'll be showing in a little bit while. So we'll also perform a simulation and see like how the state estimation is done, how the state of health estimation is done, right? So this is how we are going to be categorizing this Kalman filter. So basically, this entire thing is basically a multi-purpose Kalman filter. And it also is like very useful in terms of the BMS application point of view, because basically this is not your traditional Kalman filter, which will like take more time in order to converge. We'll come to that point a little bit later on. So basically, this is having like some few distinct advantages over the regular extended Kalman filter. Yeah. So here you can see the cell parameters. So inside, what are all the internal parameters that need to be estimated? There are actually like a lot of parameters. So like if you split up this entire internal resistance R that we see here, so we can split this up into many components like R naught. R naught stands for ohmic resistance. Ohmic resistance. Then we have R1, which is basically your polarization. Then we have C1, which is capacitance. And then we have C2, which is your second type of capacitance called as polarization capacitance. Yeah. So these are all of your battery parameters which have to be defined in detail. So what we are seeing here, these two, this is just a, like you can say, a combined representation of all of these values put together. So in the extended Kalman filter, all of these values will be estimated. So R0, R1, C1, C2, because in the true definition of parameters, this is what is meant by cell parameters. So your ohmic resistance, polarization, capacitance, and all these things. So if you combine all of these together, you can like combinedly you can represent them as internal resistance R and capacity of the cell C, right? So what is the estimation method that we can see over here? Capacity degradation method and change in internal resistance method. So your capacity degradation is always taken as a ratio between your current estimated capacity over nominal capacity, and change in internal resistance is like defined as your ratio of change in resistance between the end of life resistance and present resistance. So present resistance is your, you can say this is your estimated value, right? And then RUL, again, that is end of life resistance minus R new. So this is basically the resistance that has been obtained in fresh condition. Okay. So this is how like we are going to be defining the different cell parameters. So these are the parameters that will be updated inside the extended Kalman filter algorithm. Okay. So this is the model overview. So this is just a brief, like you can say, verbal description. So after this, we'll be like going into the model, right? So model structure, it starts in the same way. So you will see that it starts with some initialization values where we are providing initial guess of the states, initial guess of the state uncertainty, initial guess of the parameters, and along with the parameter uncertainty and also noise. Okay, so the importance of noise has to be considered. The noise has to be considered here because otherwise, like the true meaning of Kalman filter is not like truly obtained without the noise. So basically, noise is your like unwanted, like you can say, variations or deviations from the desired value. Yeah. So that also has to be inputted as the initialization values. Then, as usual, we go for prediction. So both state and parameter will be predicted. Then we go for something called as defining the sigma points. Okay, so this is a slight advancement over the existing, you can say, extended Kalman filter. So we will see that when we come to the model, what exactly is meant by sigma point. Then we go for Kalman gain, and then we go for state update, state and parameter update. Yeah. So this is the whole modeling overview, or you can say model and simulation overview. So here you can see, here is a simple Matlab script that talks about that, like basically provides the initialization values. So you can see system parameters. So all your initial values of like your SOC values, your R0 values, your initial capacity values, your noise parameters Q and R, your uncertainty, state of charge starting point, resistance, all these things have been provided over here, right? And once we run this script, the workspace variables you can see over here. This is the Matlab workspace that you can see. All of them have been registered here. And then here inside, this is the Simulink model. Here you can see like you have the parameter estimator over here. So this is where your SOC and your parameters will be estimated. So based on your estimated value, we will have a SOH estimator. So you can see here resistance is the main way through which your SOH is estimated. So one by one, we will just have a look, like a brief look inside the blocks, like each of these blocks, what exactly it contains. So here on the left side, quickly we will have a look. This is the cell temperature model. Okay, this is the, like you can, the thermal representation of the cell. Okay, and this is your equivalent cell model. This is the cell model. Okay, so utilizing the voltage that has been sensed from this, and even the SOC and the current profile, we will go into this part, that is SOC estimator. So yeah, here you can see like this is the required Kalman filter. Okay, so here you can observe the primary steps, that is prediction, correction, right? So starting with your initial values, here your initial SOC and your initial R0, you are generating a set of, like you can say, sample points, which is called as sigma points, which is basically more into the statistical analysis of the states. So basically it gives what is called as the mean and uh, standard deviation of the states, mean and standard deviation of the states. So this is like more into the bit of statistical concepts, right? So inside this, you can see how exactly the sigma points are generated. So we have the uncertainty. So you can see P here. P here is the state uncertainty, and from here onwards, your sigma points has been generated, right? So from the sigma points, we go into state prediction. Okay, so you can see here, this is your state prediction. These are your state predictions. So this is xk. Xk is your predicted state, and yk is your predicted output. Okay, your cell output. So inside this state function, we have uh, the complete the state prediction part. Okay, so in this model, we are actually going for state estimation, using the lookup tables, and then basically we are creating a matrix over here. So this is a multiplexer which is creating a matrix, and that matrix that is created will create the desired prediction function. Okay, so utilizing this, we are then going for correction. So correction is where basically your states are updated. Okay, this portion is your update state, and xk1 underscore k1, this portion is your updated state. Okay, so here further onwards from this portion, we're going to go to this x hat, where this is further split up into two parts. You can see x hat is the output here. So here there is like a simple block which actually will identify which parameter. So the first parameter is being identified here as SOC. The other parameter is being identified here as R0. Okay. So this is your predicted parameter and predicted state. So from this, we're going to go for corrected state and corrected parameter. Okay. So this is a brief overview. So utilizing that SOC and R0, which is like estimated and updated from this, we will go into this SOH estimator. So in this, so in this you can see here the same that I talked about, and that is like your R EOL minus R present divided by R EOL minus R new. Okay, so this is how the existing, you can say, the SOH has been updated. So here, this is your R present that they have estimated. This is your estimated R, that is your estimated resistance. R new has been provided from the workspace, and R end of life has been taken from the lookup table. Okay, so this is how like the SOH has been updated in this case. Okay, so we will have a quick simulation of this model. So just I will run this script here. Yeah. So when we run the model, you can see like how the graphs are here outputted. So starting with the change in state of charge over the simulation time, the change in internal resistance, and the state of health. Okay, the state of health is like you can see is going on decreasing from 100% all the way up till 70, and your ohmic resistance from the initial value of around 0.1, 0.01, It's going on increasing till 0.015. So this is your entire overview of the model. So this is a very basic model of like how you can go for SOH estimation using the Kalman filters method, right? So yeah, with this, like we'll go into the summary, right? So in summary, like till now, we have seen that your extended Kalman filter can actually, along with something called as sigma points, can be used for state and parameter estimation. So earlier, the regular extended Kalman filter only provided the state, but in this, along with the sigma points, which is like some statistical approach, uh, we are going to be going for parameter estimation as well. Yeah. So instead of following your traditional method for state linearization, which is performed in your EKF, your sigma points will generate a probability function. Okay, so this is more towards the statistics part. So in going in depth into this, actually will require like a lot more scope in terms of explaining how the statistics or mean and standard deviation, all these things come into picture. But in quick summary, the advantages are the EKF actually will not, this particular EKF that is with sigma points will not require derivation of observation metrics, which means there is no like linearization from non-linear point of view. The computation power is the same as that of EKF. It is not more, it does not require more power. And then it is also easier to implement in terms of BMS. So BMS application point of view, this can actually be implemented. Yeah. So this is your overview of the extended Kalman filter for state of health and state of charge estimation. So even the parameters is being estimated, that is internal resistance. So yeah, we are at the end of the webinar. So now, yeah, thank you for attending this.